the fundamental theorem of calculus. If f of x is a continuous function, that becomes very important, as you'll see later on, on the domain AB. And capital F of x is the antiderivative. Remember, we represent the antiderivative with a capital. On AB. Then the integral from a to b of f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. That is it. That's all it means. So what it means is you can find the antiderivative, evaluate it at b, evaluate it at a, your two endpoints, subtract them, and that gives you the area under the curve. Okay? So, so just a bit of notation here before we start practicing. I don't know if it looks complicated, but it's actually not too complicated. This bit is important though. Continuous. It has to be continuous, okay? If it's not, you get into what are called improper integrals. We don't talk about those in our class, but some you cannot find the area. We will talk about things that have vertical asymptotes briefly. So the notation is when you're evaluating the integral from a to b of f of x dx, we get the antiderivative, capital F, so this means find the antiderivative first, and then we're going to evaluate it at a and b. So then you plug in your b's and your a's. What am I missing in this that we've done every other question? We just did it on the second question on the class starter. What am I not writing in here that I've written in every other question? The c value. All right? Why am I not writing the c value? Here is why. So that's called a constant of integration, and we don't need it because if you evaluate the function, I get my antiderivative plus c, and I evaluate it from a to b. So you plug in b first. B always goes first. And you subtract the second one, and you plug in a. What happens to the c values? They disappear, right? Because it becomes constant minus constant, so they're gone. So you're just left with f of b minus f of a. So when you are doing definite integrals, you don't need to do a c value. When you're doing indefinite, you do. Okay? And remember the difference between a definite and an indefinite. A definite has these endpoints, and indefinite does not. And we're going to do both of those today. Right? They have to be the same, right? Because you're finding it for the function. And then we're just evaluating it at the endpoint. But you're right, the c's were different, but then that's two different functions. So okay, so we're gonna practice this. So the integral from 1 to 2, let's just do x squared. Nice and easy. Of x squared. So first step, find the antiderivative. What's the antiderivative of x squared? X cubed over 3. And we're going to evaluate it at 1 and 2. What goes in first? The b value, the top one. So 2. So I put 2 in. So it's 2 cubed over 3 minus 1 cubed over 3, which is 8 over 3 minus 1 over 3, 7 over 3. You're done. So what that means is, on the graph of x squared, it's graph of x squared, between 1 and 2, that area has a value of 7 over 3. That's all it means. Okay? That's it. That's the fundamental theorem. So let's try another one. X squared minus 3. So the same function's been shifted down. Okay? So we find our antiderivative, which is what? X cubed over 3 minus 3x, right? And we're evaluating that whole thing between 1 and 2. So the 2 goes in first. So it's, again, 2 cubed over 3 minus 3 times 2. And then you subtract when you put 1 in. Now, this is where everybody makes the same mistake. All right? You're subtracting 2 terms. So you need to either remember to bracket it or flip the sign in the middle. I tend to just bracket it because you're going to put the 1 into that one and the second one. Okay? People always forget to do this, and then they mess up the algebra because they forget that the sign is going to flip on the second one. And now you just have to simplify it. So 8 over 3 minus 6 minus 1 over 3 plus 3. So I get 7 over 3 minus 3. If you do this with decimals, I don't really care, but we should all be able to deal with the fractions. So that's 7 over 3 minus 9 over 3, which is negative 2/3. Does that make any sense? We have a negative, remember it's area, and we have a negative area. Do you remember me saying yesterday that if you have a negative area, it just means it's below the x-axis? And that makes sense because we took this graph and we moved it down 3 units, right? So, let me show you on Desmos, but let's do it here. And we're finding the area between 1 and 2. So it's that area there. Okay. It's not the greatest graph, but you get the point. Okay. Remember, it's from the graph to the x-axis always. Okay. Do a couple more. And then, number 3. Integral from 1 to 4 of 3 root x dx. What do I have to do with the square root first? Turn it into an exponent. And the 3, you can just kind of ignore. You can pull it out if you want. So this would be the same as the integral from 1 to 4 of x to the 1/2 dx. Just going to give you 3x to the 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So those 3's will cancel. So I get 2x to the 3/2 evaluated from 1 and 4. You can pull the 2 out or you can leave it in. It's up to you. So you could write 2 and then go 4 to the 3/2 minus 1 to the 3/2 like that. Or you could have the 2 with both of those. It doesn't matter. What does power of a half mean? It means square root, right? So 4 square rooted is, cubed is 8. So this becomes 8 minus 1, which is 7 times 2, and 14 is your answer. All right. Okay? So the antiderivative stuff is the exact same, except now, once you get the antiderivative, you have to evaluate it at the endpoints, and you subtract those answers to get the value of the area under the curve. Okay? The questions I would like you to try, which will take us up to the break. Page 288, 5 to 21, please. And I think you should do 29 as well. Please. When we did the definition of the fundamental theorem, we said f of x has to be continuous on the interval AB. So why is that important? If we look at this function here, x minus 3, and by the way, you can go into Desmos and use the integral, and it will actually give you the answer, so you can check your work. But this is essentially saying x minus 3 is a straight line between 1 and 2. So it makes sense we get a negative number. It's 1.5, negative 1.5, because it's below the x-axis. Now, if I take that function, x minus 3, I put it over x, we created a vertical asymptote, right? Everybody agree? At 0. But, so if I put that into the integral here, I will still get an answer because it's outside of our domain, right? Our domain is between 1 and 2, and the vertical asymptote is at 0. But if I change this to x minus 1, there is no answer for the integral. Okay? Because that asymptote, that vertical asymptote, is inside of our domain. Okay? If I said it was 1.5, it would still be the same thing. Why did it give me 1.5 as 1? That's wrong. Desmos is wrong, people. Desmos is wrong. There are, well, I shouldn't say Desmos is wrong. There are these are called improper integrals, and some of them converge to give you an answer. We do not study them. So if you see a vertical asymptote, it doesn't work, okay? Now, why it doesn't work is because remember yesterday when we were looking at the rectangles, okay? You're doing the height of the rectangle. So if you're drawing the graph, if I'm going to draw a rectangle here, how high is the rectangle? Because this goes on forever. You never can get to that point, okay? So you can't actually make the rectangle, right? So that's why the integral is undefined. There is no answer if you have a vertical asymptote in your domain, okay? If you want to look at what improper integrals are, they're in chapter 8, 8.8. That is not part of this course. That's Math 101. And it combines limits and integration and all these other things that we've learned so far. We're not doing that. So if you see a vertical asymptote in your domain, it does not exist. Okay? So the clue is always look at the bottom. If you have a variable in the denominator, you have to see where the vertical asymptote is. If it lines up in your domain, then it's no good. Okay? All right. Now we're going to do integration by substitution. So we'll do indefinite first, and then we'll do definite. Whoa. Okay. Substitution. If we have this integral, all right. So this looks nothing like what we've seen. Okay. What could we do? What would you do if I gave you this right now without knowing what substitution is? What could you do to solve this? Sorry? Okay, so we can take the constant out. You can't put the x into here because that means there's 3 of those things. No, I mean, like the x outside of the bracket. But I still have it. Oh, okay. So still inside the squiggly, the integral sign? Okay, so you can do that, but then we're still stuck with this and this and this. Right now we only know how to do polynomials. Okay, so you could multiply this out. X squared plus 1 times x squared plus 1 times x squared plus 1 times x, or 2x. That's going to take forever. But you could do that. But there is a faster way to do this, and it's called substitution. So what you do, we call it U substitution, the book, but you can use any variable you want, okay? We want to get rid of the most complex part, essentially. Okay, now that's not a hard and fast rule, but what would be the most complex part of this? There's 2 parts, there's this and there's this. What's more complex? X squared plus 1. And what you should do is when you look at this, you'll see in a sec why you want to do this. Quickly do the derivative of both. What's the derivative of this? 2x, right? If you see that showing up somewhere else, that is what you want to do your substitution on. Okay? So u is going to be x squared plus 1. Then we're going to take the derivative. And so we go, okay, du dx is equal to 2x. The whole point here is to get rid of all the x's over here. So I'm going to multiply the dx up and get du is equal to 2x dx. Because we want to make a new integral in terms of u. So now you can see that this is right there. So this integral now becomes, instead of x squared plus 1, we said that x squared plus 1 was equal to u. So that becomes u cubed. And then 2x dx is equal to du. So now we've created a different integral that is much simpler in terms of u's. And we can now integrate this. So if I just said, what's the integral of u cubed? U to the 4 over 4. We have to put a plus c because this is an indefinite, right? There's no endpoints. All right. The last step is to get rid of the u. So sub out. Instead of having u here, we said u is equal to this. So you put that back into there, and you get x squared plus 1 all to the 4 over 4 plus c. That is the integral, or the antiderivative, sorry, of this. If you took the derivative of this, you would get that. And you can check it, because if I did the derivative, you don't have to write this. If I did the derivative of this, you'd use chain rule. The 4 would fall down, x squared plus 1, take away 1, times the inside derivative, which is 2x, and those cancel, and there's your derivative, okay? Or your derivative. All right, so the whole point of u substitution is to turn this integral into something that just has u's. You want to get rid of all the x's, okay? And so when you first look at it, you always look, usually 99% of the time, you're substituting out what's in the bracket, okay? Quickly in your head, you do your derivative, that's 2x, and it kind of matches that. All right, so you know you're on the right track. If you do the work and it doesn't work out, you just make a different substitution. And that'll, when we get into more complex ones, that'll be something that we have to look at. So let's try another one here. Number 2. Integral. X squared, 6 minus x cubed, all to the power of 5 dx. All right, what's u going to be? Yeah, what's in the bracket? So u, 6 minus x cubed. Take the derivative. Du over dx equals minus 3x squared. If I multiply the dx up, I get that. Now, is there anything in our integral that looks exactly like this? No, but what is there? There's an x squared in the dx. So if I divide off that -3, I get that. So this and this equals du over -3. We've already said that what's in here is u. So this whole integral now becomes u to the power of 5 du over -3. Okay, how do I solve this now? What can I pull out of the integral? Yeah, -1/3. So we pull out a -1/3. And then we're just dealing with u to the 5 du. Which is what? What's the antiderivative of that? U to the 6 over 6 plus c, which is -u to the 6 over 18 plus c. Your final step is to put back in what u was. So it's 6 minus x cubed. Sorry? Oh, sorry, thank you. Thanks. Yep, to the power of 6. And there you go. And you can always check it by doing the derivative, which I'm not going to do. Maybe a couple more here to do. We okay so far? It's kind of just practice here. So what if we have a trig one? So we do the integral of cos 5x dx. So yes, so we've only done stuff where we just have x's right now, right? But now I've put a number in there. So that is always going to be your substitution. U is equal to 5x. So what's du? It's going to be 5, right? Du dx is going to be 5. So I'm just going to write it as 5 dx. I multiply the dx up to the other side. Is there a 5 dx in your integral? Right? Because this, that's all tied up in there. So you have to divide off that 5. And there's a dx in your integral. So this is du over 5. That is u. So the new integral is now cos of u du over 5. What do I pull out? 1/5 comes out. What's the antiderivative of cosine u? Just sine of u, right? Because the derivative of sine is cosine. All right, so it's 1/5 sine of u. What was u? 5x, so it's 1/5 sine of 5x. Remember to tack on your plus c, and you're done. All right, I think we need to do let's do one more. Integral t to the 4 square root 2t to the 5th plus 5 dt. All right, what is u going to be? All the stuff inside the square root. So u is equal to 2t to the 5th plus 5. What's du? Ten t to the 4 dt. What do I need to do? Divide off the 10, because those two things are what I need to get rid of, because all the inside here is already u. So du over 10 is t to the 4 dt. So my new integral is now u. I'm going to write it as the 1/2 because it's square rooted. And t4 dt is equal to du over 10. We okay? All right, take the 1/10 out. And then you add 1, 3 over 2, which is the same as multiplying by 2 over 3. So I get u to the 3/2 over 5. Over 15, sorry. That makes more sense. And then sub back in what u was. $20. Where's 20? That's a 2. That's a u, sorry. Over 15 plus c. Okay, so u is 9 for now. Most of the time, it's going to be what's inside either the square root, the cube root, the brackets raised to some exponent. You write it out, you take the derivative, you're going to have to manipulate this to make it match some stuff that's in here. You do all your substitutions to generate this straightforward integral. Usually it's a polynomial. You evaluate that. You plug back in what u was, and just don't forget to put your plus c because these are all indefinite integrals. Okay? Questions I would like you to do are on page 301, numbers 5 to 21, please. Odd. Now, so we look at this question, x times root 2x minus 1. That has a degree of 1, that has a degree of 1. Okay? So we still have to use our substitution. Okay? So if we substitute in what's inside the square root, and then we do the derivative, we get that. We divide off the 2. So we get du over 2 is equal to dx. So now, this here is du over 2. That is u. But what's the problem? We still have this x here. You can't have two variables. Okay? You can only have one. So we need to get rid of that x. We need to figure out a way to make a substitution on the x. How can that involves u? How can we do that? Based on what we have over here. You can take this and solve for x. So if I move the 1 over and divide by 2, I get u plus 1 over 2 equals x. And now that can be subbed in. So this bit here is now u plus 1 over 2. So now we got to clean up the integral. So we're going to rewrite it and then clean it up. So this integral now becomes u plus 1 over 2 times u to the power of a half, that's the square root bit, and dx is du over 2. Which looks kind of gross, but it's not too bad, because what can we pull out? One half, pull out a fourth, right? Well, there's a 2 and a 2, right? There's two 2's. So I can pull 1/4 out. And I'm left with u plus 1 times u to the half du. We don't like that, so what am I going to do here? Multiply it in. Multiply this in there. But when you're multiplying, what do you need to remember? What do you do with the exponents? You add them. So u to the half times u is u to the 3/2, and u to the half times 1 is just u to the half du. That is an integral we can deal with. So 1/4 stays there. U to the 3/2 plus 1. So plus 2 over 2 is 5/2. You divide by your new exponent. If you're dividing by 5/2, that's the same as multiplying by 2 over 5. Plus add 1 to u to the 1/2, u to the 3/2. 2/3. You can leave it like that. Or actually, you can't. Because we have to put what back in? Put back in what u was, which is 2x minus 1. And then you're done. So we get, you don't have to multiply the quarter in. You can if you want to, but. So it's 2 times 2x minus 1 to the power of 5/2 over 5 plus 2 times 3/2 over 3 tack on your plus c, and you are done. Okay? So when you see one where the degrees are the same, it probably means you're going to have to solve for x and sub that in as well. Okay? All right, let's do one of these with substitution, or with a definite integral. So we'll do this one. 0 to 1. Teacher. So does this look like the one we just did? Or does this look like the nice ones that we did before? The nice ones, right? Because inside is x squared. So if you take the derivative, you're going to get 2x. Yes. That's a 0, sorry. Yeah, we've been writing a lot of u's. So this is a definite integral. So we're going to go, okay, u is equal to what? X squared plus 1. Du is equal to 2x dx. So I get that, which then we sub into the integral, and I get u cubed du over 2. Okay, now this is where you have a choice. All right? This is a definite integral, which means we're going to get a number at the end of this. So you have a choice of now evaluating this. So I'll do it quickly. You don't have to write this down because it's not the way I would do it. You can evaluate this and go, that's u to the 4 over 4 times 2 is 8. And then sub back in this, which gives me x squared plus 1 over 8. And since it's a definite integral, we're evaluating it between 0 and 1. Okay? And then you plug that in. I'll just do it. 1 squared plus 1 over 8 minus 0 squared plus 1 over 8, which is 1/8 minus 1, 2/8 minus 1/8, which is 1/8. Okay? That's what you do. Or, and this is what I would recommend that you do, you can just evaluate this. But what we have to do is, because these are x values, right? Because our integrals were in terms of x, we have to change them to u values, which is not bad, because this says when x is 1, x is 0. So when x equals 0, what does u equal if I use this? 1. So now my lower would become 1. And if x is equal to 1, u is equal to 2. So these two integrals will produce the same answer. Yes? They won't always be that. So this is an x value, right? So if I put that into here, 0 squared plus 1 gives me 1. If I put the 1 in, 1 squared plus 1 is 2. That's all I'm saying. So then if I evaluate this integral, I get u to the 4 over 8 evaluated from 2 and 1. Oh, you know what I forgot? That's to the power of 4. So it's like going to be a 1/8. I'll just write it like this. There, it'll be that. Okay. Then I put in my 2. I subtract putting in the 1. Whatever that is, I don't actually care. The point is, it gives you the same answer. Okay? So when you're doing a substitution with a definite integral, you have a choice. You can evaluate it, sub back in what the original was, and then evaluate it at the original 2 endpoints. Or when you convert the integral to a u, you change the endpoints to u values using your substitution here, and just evaluate that. It's usually faster to do that. Okay? So let's do one more, and then that'll be it for today. Oh, I would. I'm lazy right now, that's all. No, that would be a number. 2 to the 4 is, what is that, 16? So 15 over 8 would be your answer. Okay, so let's do, I don't know. Let's just do one from the book here. Number 2. The integral from 0 to 1. And you'll notice they usually pick nice, easy numbers. Okay, so there's our integral. Is this going to be a nice one that works out? Yeah, right? Because we got 2x to the 4 and the outside is an x cubed. Do you want me to let you try it? And then I'll put up my answer. Are we done? I can. I'll find some stuff. You ready for the answer? 13/12? Or 1.083 repeating? Is that what people got? Perfect. And if you look at the graph, Desmos actually gets this one right. 1.083 repeating. That's the graph. So excluding certain vertical asymptotes that Desmos doesn't seem to understand, it is a good way to check your answer. Or there's a whole bunch of other integration apps out there. Okay. I think that's enough for today. I'll give you a couple questions to practice, and I'll post a key for the quiz. So questions on this stuff would be page 302, numbers 47, 49, and 55 to 61 odd.